let me change the slide. First of all, thank you, Joseph, for the nice introduction. And thank you all for being here. It's my great pleasure to share my research with you, and I hope you enjoy. So when I say turbulence, what comes to your mind? Perhaps one of the first things would be a bumpy airplane ride. But turbulence is not limited to the sky, rather we are surrounded by it in our daily lives. For example, you can easily observe turbulence in the Limmat, especially when water flows around a boat. And also, think of the smoke from a lit candle. It starts off smooth and quickly becomes turbulent. As you may guess from this example, turbulence refers to a chaotic motion of fluids, and the chaotic nature makes the prediction of fluid flow very challenging. Nonetheless, understanding turbulent flow is crucial across various fields, such as meteorology, aerodynamics, and engineering. So to study turbulent flows, one first needs to understand how turbulence occurs. So let's do the following thought experiment. You have two identical cups. One is filled with water and the other with honey. If you stir them rapidly with the same speed, water will show more chaotic behavior than honey because it is less viscous. So indeed, fluids with lower viscosity tends to be more turbulent. In addition to viscosity, also velocity and length scale play an important role in distinguishing turbulent flows. So in 1883, Reynolds conducted the following famous experiment where he studied the behavior of fluid flow, the water especially, inside a glass pipe by adding dye to the flow. And he observed the following. When the velocity is low, the stream of dye remains smooth. While he increased the velocity, the flow becomes turbulent. So from this experiment, he introduced a quantity which is a combination of velocity scale, capital U, and length scale, capital L, and viscosity nu, which is called Reynolds number. And he observed that at sufficiently high Reynolds number, fluid flows become turbulent. For this reason, phenomena in turbulence have been observed by increasing Reynolds number, and they are formalized in the limit of Reynolds number going to infinity. Okay, then what do we know about turbulence? Turbulent flows by nature are chaotic, so it is hard to study one particular instance. Rather, we want to understand how they behave on average. So over time, many experiments and numerical simulations have identified the fundamental features of turbulence, and especially based on early experimental findings in 1941, Kolmogorov established a statistical theory of turbulence. However, from mathematical standpoint, we haven't yet achieved unconditional verification of this phenomena. So connecting phenomenological or statistical theory with mathematics still remain as a major challenge in the field. But the thing is that we don't even have a one single explicit example that reflects fundamental features of turbulence. So my goal is to find such examples, and through which I wish to gain some insights into turbulence. So from now on, let me first talk about how we can describe fluid flow mathematically, and then I'll move on to the features of turbulence. Okay, so for the simplicity, let me assume few things. First, we have fluid inside a periodic box so that we can stay away from the physical boundary. Indeed, the turbulence that I'm going to talk today is the one which is away from the boundary. And second, there's no external force in the system. And third, we restrict our attention to the incompressible fluids. So you can think of water instead of air. More precisely, we assume that the density of fluids remains constant everywhere in the domain. Under these assumptions, fluid flow can be described by velocity and pressure only. When I say velocity at each fixed time, you can think of a vector field, while for the pressure, it will be a real valued function. Now, taking these as unknowns, one can derive the equations simply from the mass and momentum conservation. So first equation is called momentum equation. And if you look at the left-hand side term, it describes the acceleration of a fluid particle, and that balance with the force acting on it. Since water flows from the area of high pressure to the area of low pressure, you can imagine that there is a force in the direction of minus gradient P. On the other hand, divergence-free condition explains the incompressibility, which can be simply derived from the mass conservation. So these equations together, called the Euler equations, and it's obviously derived from Leonhard Euler, who is a Swiss mathematician, in 1757. But in 19th century, Navier and Stokes independently noticed that the effect of the internal friction is significant. So they incorporate the additional red color term to the Euler equation, and nowadays these equations are called the Navier-Stokes equations. Now, if you look at this new term, in front of Laplacian, there is a parameter which describes the viscosity. This makes sense because if you have fluid with larger viscosity, the effect of friction will be stronger. But since real-world fluids are independent of the choice of the unit and dimension, one can also consider non-dimensionalized Navier-Stokes equation, which is given as follows. So here, the viscosity is simply replaced by the inverse, the reciprocal of the Reynolds number. So from this explanation, you can easily see that Navier-Stokes equations better describe the real-world fluid flow. But on the other hand, remember that turbulence regimes are identified by sending Reynolds number to infinity. And if you do that, Navier-Stokes equations formally converges to the Euler equations. So in this context, Euler flows also have their own significance, serving as approximation of turbulent flows at sufficiently high Reynolds number. Now, let me move on to the fundamental features of turbulence. One of the most fundamental one would be anomalous dissipation. Here is what it means. If you stir honey in a cup and then let it be, then you would expect the motion of fluids slow down over time because the friction between fluid layer leads to a dissipation of kinetic energy. But now my question is, how quickly does the energy dissipate? If you do the same experiment with water, then the dissipation would be much slower because water is less viscous. So you may expect the following: as Reynolds number converges to infinity, the dissipation rate decreases and eventually converges to zero. And in fact, one can compute the dissipation rate of total kinetic energy by using equation. So let's assume we have a solution, smooth solutions to the fluid equation. And we do the following. Well, since kinetic energy is the half of the mass times velocity square, if you put density is equal to 1, then total kinetic energy, which refers to the summation of kinetic energy over the entire domain, can be described by a half of the square integral of the velocity. And now to see its dissipation rate, if you take time derivative, it balances with the following terms. So in the presence of the friction, From the Navier-Stokes equation, you obtain the following term, which arising from the term which describes friction. So the friction really leads to the dissipation of total kinetic energy. On the other hand, in the absence of friction, from the Euler equation, you have zero dissipation rate. So from this, the expectation sounds very reasonable. However, in turbulent flows, this is no longer the case. In fact, if you measure the dissipation rate of total kinetic energy and send Reynolds number to infinity, it does not converge to zero, rather it converges to some strict positive number. This means that turbulence have a sub-mechanism of dissipating energy, and such dissipation is so strange that it is called anomalous dissipation. Okay, so now let me move on to the mechanism behind the anomalous dissipation, which can be understood through a concept of energy cascade. To explain this, let's imagine our fluid flows consisting of different sizes of eddies. By eddy, I mean a circular motion of fluids. So for example, if you stir water in a cup, then you create large eddies of the size of the cup. But if your flows are turbulent, these eddies will break into the smaller one, and the smaller eddy will break into even tinier one. And throughout this process, kinetic energy will be transferred from large scale to smaller scale, which is called energy cascade. But note that this process doesn't involve the internal friction. Only when you reach a sufficiently small scale where the friction comes into play, the eddy loses its energy and dissipates. Now, let's think about what happens if we increase the Reynolds number. Then the scale where the dissipation comes into play becomes much smaller. So the energy cascade continues for a longer period, creating even smaller size of eddies. And now let's go back to the dissipation rate of total kinetic energy. From the equation, the dissipation rate balanced with the following term. And now if you send the Reynolds number to infinity, the factor in front will converge to zero, but will have larger derivative due to a creation of small size of eddy. So this large derivative will balance with the small factor in front, which prevents the limit from converging to zero. So this results in the anomalous dissipation. Now let me talk about the second feature of turbulence, which is called intermittency. To explain this, let me start with self-similarity. In general, self-similarity refers to the following property. As illustrated by Sierpinski's triangle, if you zoom in certain parts, the magnification looks like the whole. In Kolmogorov's theory, he assumed the self-similarity of turbulent flows in statistical sense, which means the following. He considered the velocity increment, denoted by delta U here, when the displacement vector L is in the inertia range, meaning that the range where the energy cascade occurs so that the turbulence is effective. And he said the following. If you choose arbitrary point in a fluid, and then zoom in this velocity increment with a certain rescaling factor, then this rescaled velocity increment will satisfy the same statistical property with the original one. So this is the Kolmogorov self-similarity hypothesis, but it turns out that this doesn't seem to be true in the real world. So now to see this, let me introduce the peace moment of the velocity increment, which exhibits consistent power law in turbulent flows. So from now, let me call this function of the displacement the structure function. All right. Then under the self-similarity hypothesis, one can compute the exponent in the structure function, which will be given by P over 3. And now if you draw the graph for this exponent, zeta p, it will be illustrated by the following, the black straight line. However, as you see from this colored line obtained from the experimental result, a deviation is observed unless p is equal to 3 in the real world. So such deviation is called intermittency, and it really supports the non-self-similarity of the turbulent flows. So these days, we now believe the turbulent flows are intermittent rather than self-similar. For later use, here we need to remember two things. When p is equal to 3, we want the exponent to be really matches with the Kolmogorov prediction. But while p is not equal to 3, we expect deviation. Okay. And now let me recall my goal. I said I want to find a mathematical example that reflects all fundamental features of turbulence. And in this direction, one of the major open problem in the field is the following. Can we find an example which reflects the anomalous dissipation, which is the most fundamental feature? More precisely, one can ask the following. Are there any sequence of physically meaningful solution to the Navier-Stokes equations that satisfies the following property? This problem still remains open, but over the past decades, we had some exciting progress. So from now on, let me talk about it. All right, so one example is the resolution of the Onsager's conjecture. So based on his understanding on the anomalous dissipation energy cascade, Onsager considered the extreme case that Reynolds number is equal to infinity, although this is not possible in the real world. And he said the following, that turbulent flows in this hypothetical situation, which refers to the ideal turbulent flows, will exhibit total kinetic energy dissipation. This means that mathematically one can find a solution to the Euler equation whose total kinetic energy dissipates. And he added the following comment. Since smooth solution to the Euler equation always conserve total kinetic energy, one may worry about a contradiction. But this is not the case because ideal turbulent flows will not be smooth. In fact, he even proposed what should be the critical amount of smoothness for the energy conservation, which was known as Onsager's conjecture, but now with proof, it is called Onsager theorem. Okay, so let's look at the precise statement. To quantify the smoothness, Onsager used the following fractional differentiability. As you know, when alpha is equal to 1, it essentially corresponds to the usual differentiability. So one can view this condition as fractional differentiability when alpha is between 0 and 1. And then what Onsager proposed is the following. Alpha equal to 1/3 is the critical number for the energy conservation. More precisely, if you have a solution to the Euler equation which satisfies this fractional differentiability condition for alpha greater than 1/3, then total kinetic energy conservation is always guaranteed, while alpha is less than 1/3, conservation may fail. In other words, you can find a solution whose total kinetic energy dissipates. The conservation part was already proven in 1990s, but non-conservation parts was built on a series of works spanning over like 3 decades. But eventually, Phil Iset gave a full proof. Okay, now let me connect this fractional differentiability condition with the structure function. So if you have a solution which satisfies the following fractional differentiability condition, then the associated structure function will have the following graph of exponent, a straight line with the slope alpha. And so according to Onsager's theorem, alpha equal to 1/3 line will be the critical line, and this line matches with the original Kolmogorov's prediction. So in this context, the construction for the non-conservative part is particularly meaningful because we now have an explicit solution to the Euler equation, which exhibit the fundamental features of ideal turbulence, which is total kinetic energy. And when P is equal to 3, the exponent really matches with the Kolmogorov prediction, although the deviation doesn't happen. So now one may ask the following question. So are these constructed solutions physical? In other words, one can ask, are they aligned with other physical laws or other features of turbulence? Unfortunately, there are two features that the constructed solution don't agree with. One is, as you've seen from the structure function graph, the constructed solutions are not intermittent. And second, the solution creates kinetic energy in some local region, which is not possible in the real world. So since I've already talked about intermittency, let me add a few more words for local evolution of kinetic energy. So obviously, the Onsager theorem only takes into account the total kinetic energy, but to talk about physically meaningful solutions, one has to understand what happens with kinetic energy in every local region. So let's take some arbitrary region in the periodic box colored in yellow here. For smooth solution, again, we expect local energy conservation, meaning that if you consider the change of kinetic energy in this restricted region, the change must be balanced with the change through the boundary. In other words, there's no essential creation or dissipation of kinetic energy. On the other hand, in turbulent flows, extra dissipation may occur. So now let me describe this mathematically. Here, equality corresponds to the local kinetic energy conservation, while strict inequality corresponds to a strict dissipation. Together, this inequality is called local energy inequality. And a physically meaningful solution to the Euler equation must satisfy this condition. So one can view this condition as an admissibility condition for a physical solution to the Euler equation. All right, so for these reasons, after the resolution of the Onsager's conjecture, strong Onsager conjecture had been studied, which essentially combines the Onsager theorem with the local energy inequality. So if you look at the theorem, again, we consider the fractional differentiability to quantify the smoothness. And again, alpha equal to 1/3 is the critical line. More precisely, if alpha is greater than 1/3, now we require the local energy conservation. While alpha is less than 1/3, we want to find a solution which not only satisfy the total kinetic energy dissipation, but also satisfy the local energy inequality. The conservation part was already obtained in 2000 by Duchon and Robert, but non-conservation part still remain as an open problem. Although we have some partial results, but among them, the current best partial results was obtained by Drellis and myself in 2020, covering the range alpha less than 1/7. So we are still away from 1/3. Okay, but if you look at this conjecture, you may also ask the following question. This conjecture doesn't seem to capture the intermittent nature of turbulence. So can you incorporate the intermittency? So this motivates us to consider strong Onsager conjecture in L3 framework. And together with my collaborators, Giri and Nova, we are able to fully resolve it. So here's what we obtained. We constructed a solution to the Euler equation, which satisfy the total kinetic energy dissipation and local energy inequality, as well as the intermittency. In particular, if you look at the associated structure function, the graph of its exponent can be described by the following. When P is equal to 3, it almost matches with the Kolmogorov's prediction, but when P is greater than 3, the obvious deviation occurs. So from this perspective, our constructive solution would be meaningful because it reflects the two fundamental features of ideal turbulence. At the same time, it satisfies the admissibility condition for physical solution to the Euler equation. And perhaps what's left is we want to show that the solution can be realized by the limit of Navier-Stokes flows as Reynolds number going to infinity. Okay, so this is end of my talk. I hope you get a glimpse of turbulence. And in case that you are wondering about the picture from the first slide, this is a drawing of Leonardo da Vinci, who actually coined the term turbulence. So you can see how old the subject is. Thank you for your attention.